The F-35's radar cross-section, about the size of a marble, gave Navy pilots a decisive edge, allowing them to slip through Yemen's most fortified airspace undetected. One pilot described the experience as surreal, flying invisibly past radar systems designed to spot objects 100 times larger without triggering a single alert. Iran has equipped the Houthis with P-12 and Fanong radar systems, but these 1970s-era technologies were no match for the F-35's stealth. The radar-absorbing materials and angular design rendered the systems effectively blind, highlighting the stark technological gap and underscoring the mission's critical role in reshaping the balance of power. The F-35C's stealth design. Modern radar systems typically detect aircraft with cross-sections exceeding 1 square meter, but the F-35C's signature measures just 0.005 square meters. This stealth capability results from decades of innovation, combining advanced materials, precise engineering, and aerodynamic design. Unlike early stealth aircraft like the F-117, which sacrificed maneuverability and payload, the F-35C integrates low observability with multi-role combat performance, representing a leap forward in stealth technology since the Gulf War. The F-35C's stealth features can be thought of as making it a ghost in the sky, evading detection through a combination of design elements. Angular airframe geometry. Surfaces deflect radar waves away from their source, reducing detection. Radar-absorbent materials. Coatings convert radar energy into heat, covering 90% of the aircraft, especially critical areas like leading edges. Engine nozzle design. A sawtooth-patterned edge minimizes radar and infrared signatures. Diverterless supersonic inlets. These eliminate traditional radar reflective points while managing airflow efficiently. These features work together seamlessly, ensuring the F-35C maintains its stealth profile even during aggressive maneuvers. Continuous surface curvature and jagged skin panels minimize radar returns regardless of orientation, allowing the aircraft to operate undetected in contested environments. Operational benefits extend beyond stealth. Carbon fiber composites, making up 35% of the airframe, provide the strength needed for carrier operations while preserving stealth characteristics. This durability ensures the aircraft withstands the stresses of catapult launches and arrested landings without compromising radar deflection. Maintenance improvements, such as a more durable radar-absorbing skin, reduce logistical burdens and enable faster mission turnarounds, critical for high-tempo operations. The F-35C's stealth isn't limited to radar evasion. Infrared and visual signature management, along with controlled electronic emissions, further enhance its ability to penetrate advanced air defense networks. In Yemen, for example, the aircraft approached targets undetected, bypassing legacy radar systems without requiring electronic warfare support. This comprehensive approach to stealth allows the F-35C to perform multiple roles simultaneously, demonstrating its value in combat. Operational testing confirms its ability to defeat air defense systems that challenge fourth-generation fighters, solidifying its position as a cutting-edge platform in modern warfare. Precision strike capabilities. The F-35C's precision strike capabilities faced their ultimate test against hardened Houthi targets embedded in Yemen's mountainous terrain. These missile sites, often concealed beneath layers of rock and earth, posed a significant challenge. The aircraft's ability to carry specialized munitions internally while maintaining stealth was critical to the mission's success. Unlike older fighters that relied on external ordnance, the F-35C delivered bunker-busting weapons without compromising its low observable characteristics. The BLU-109 penetrator warhead, designed to neutralize underground facilities, played a key role. Its hardened steel casing and delayed detonation sequence ensured maximum impact within fortified structures. Similarly, the GBU-31 Joint Direct Attack Munition, JDM, provided pinpoint accuracy against surface targets, guided by a GPS INS system capable of striking within meters of the intended point. These weapons allowed the F-35C to destroy heavily fortified sites with precision, minimizing collateral damage. During one strike, the F-35C targeted a Houthi missile site hidden beneath a rocky outcrop. Using its electro-optical targeting system, EOTS, the aircraft identified the camouflaged entrance from over 12 miles away. The BLU-109 penetrated the reinforced bunker, detonating deep underground to neutralize the facility. This operation highlighted the synergy between advanced sensors and precision munitions, enabling success in a complex environment. The F-35C's internal weapons bays, each with 2 stations, allowed it to carry multiple precision munitions while maintaining stealth. For less contested environments, external hardpoints enabled beast mode configurations with heavier payloads. This flexibility meant a single F-35C could perform missions that previously required multiple aircraft types. Transitioning between these configurations ensured adaptability across varying threat levels. The Yemen operation also demonstrated how modern precision weapons reduce collateral damage. GPS-guided JDAMs struck within meters of their targets, while the BLU-109's controlled detonation minimized surface destruction. Advanced mission planning systems integrated with the F-35's avionics allowed real-time adjustments to weapon parameters, ensuring effectiveness even as intelligence evolved mid-mission. By combining stealth, precision, and adaptability, the F-35C redefined operational possibilities. The Yemen mission validated its ability to neutralize hardened targets with minimal support, showcasing a leap forward in modern air combat capabilities. Electronic warfare integration. Stealth alone cannot guarantee survival against modern integrated air defense systems. The F-35C's operation in Yemen demonstrated how electronic warfare platforms like the EA-18G Growler provide critical support against dense surface-to-air missile networks. Early combat experiences in Syria revealed limitations when 5th-generation aircraft operated without dedicated electronic attack support, prompting changes in operational doctrine. The Growler's capabilities bridge this gap, enabling stealth aircraft to operate effectively even against advanced threats. The EA-18G Growler carries the ALQ-249 next-generation jammer, a system that acts like an electronic shield, disrupting enemy radar systems and blinding their ability to track aircraft. Covering a wide frequency range with a 10-fold power increase over previous systems, it can precisely target threat emitters while minimizing detection risk. During the Yemen operation, the ALQ-249 simultaneously disrupted multiple radar systems, preventing coordinated tracking of the F-35C strike package. Its ability to burn out radar control circuits proved particularly effective against older systems like the Fansong radar used with SA-2 missile batteries. AGM-88G's ARGM-ER missiles complement the Growler's jamming by physically destroying enemy radars. These advanced anti-radiation missiles can locate and engage emitters even after they shut down, using inertial navigation and GPS guidance. With a Mach 2 speed and 93-mile range, they allow Growlers to engage threats from a safe distance. In Yemen, these missiles destroyed at least one Fansong radar installation, eliminating a key node in the Houthi air defense network. Networked warfare systems enable Growlers to share electronic warfare data with F-35Cs in real time, creating a synergistic effect. The F-35's sensors detect radar emissions, which the Growler then targets for suppression or destruction. This coordination allowed rapid adaptation to emerging threats during the Yemen strikes, ensuring mission success. The Yemen operation validated the importance of integrated electronic warfare in modern air combat. The combination of F-35C stealth and Growler electronic attack neutralized dense air defense networks without losses. This partnership highlights how 5th-generation aircraft achieve their full potential when supported by dedicated electronic warfare platforms, a critical integration for maintaining air superiority in contested environments. Sensor fusion advantage. Locating concealed missile sites in Yemen's mountainous terrain required advanced technology to overcome the limitations of traditional reconnaissance. The F-35C's sensor fusion architecture acted like a digital brain, seamlessly integrating data from multiple onboard systems into a single coherent tactical picture. This innovation reduced the cognitive workload for pilots, enabling faster and more accurate target identification and engagement. At the core of this system was the AN/AAQ-37 Distributed Aperture System DAS, which used 6 infrared cameras to provide uninterrupted 360-degree coverage. This allowed the aircraft to detect heat signatures from hidden threats. Even in Yemen's rugged topography, the DAS could simultaneously track multiple targets and monitor incoming missile threats without requiring manual sensor adjustments, ensuring constant situational awareness. The AN/APG-81 AESA radar complemented the DAS by delivering precise terrain mapping while maintaining a low probability of detection. Its ability to perform multiple functions, such as scanning for air contacts, mapping ground targets, and supporting electronic warfare, meant the F-35C could operate covertly. The radar's synthetic aperture mode produced high-resolution ground maps, even through clouds or darkness, making it invaluable for identifying camouflaged facilities. Adding another layer of capability, the Electro-Optical Targeting System, EOTS, combined infrared and laser designation functions. With a range exceeding 12 miles, EOTS enabled pilots to confirm targets like concealed bunkers or mobile launchers before entering high-risk zones. Unlike older systems, EOTS integrated seamlessly with the F-35's fusion architecture, automatically correlating its data with other sensors for a complete operational picture. Mission computers process these sensor feeds using algorithms to prioritize and flag anomalies in terrain that could indicate hidden structures. This automation drastically reduced the time needed to identify targets compared to manual methods. Pilots received synthesized, actionable information through intuitive cockpit displays, allowing them to focus on decision-making rather than data interpretation. The Yemen operation showcased how sensor fusion compressed the kill chain, enabling F-35Cs to locate and engage concealed targets in a single sortie. By transforming raw data into a unified tactical picture, the system provided a decisive edge, demonstrating how this integrated approach redefines modern air combat operations. Carrier operations complexity. Operating fifth-generation stealth aircraft from an aircraft carrier presents unique engineering challenges that demand specialized modifications. The USS Abraham Lincoln served as the launch platform for the Yemen strikes, demonstrating how naval aviation extends the reach of precision strike capabilities. Carrier operations require careful balancing between maintaining stealth characteristics and ensuring structural durability in the harsh maritime environment. These competing demands shaped the F-35C's design from its earliest development phases. The F-35C incorporates several key modifications distinguishing it from land-based variants. Its wingspan measures 13.1 meters compared to the F-35A's 10.7 meters, providing 42% more wing area for improved low-speed handling characteristics. This expanded wing surface generates additional lift during catapult launches and arrested landings, crucial for operating within the confined space of a carrier deck. Larger control surfaces enhance stability during approach phases, ensuring precise glide paths for successful recoveries. Structural reinforcements throughout the airframe accommodate the extreme stresses of carrier operations. The landing gear features heavy-duty shock absorbers and larger tires to withstand the impact of arrested landings, which can generate deceleration forces exceeding 4 Gs. The tailhook mechanism connects directly to the aircraft's primary structure, distributing arresting forces efficiently. These modifications, while adding weight, are essential for carrier suitability. To combat saltwater corrosion, the F-35C employs specialized coatings, gold-plated electrical connectors, and corrosion-resistant alloys. Maintenance crews perform regular freshwater rinses and inspections to prevent degradation. These measures ensure the aircraft remains mission-ready despite the maritime environment's challenges. Stealth characteristics remain uncompromised. Radar cross-section reduction features such as sawtooth panel edges and radar-absorbent materials are carefully integrated with carrier-specific adaptations. The wider wing folds at precise angles to maintain a low, observable profile when stowed below decks, preserving stealth parity with land-based variants. Deck crews face unique challenges in handling the F-35C. From managing its sensitive stealth coatings to coordinating rapid turnarounds, their expertise ensures the aircraft operates at peak performance. Extensive training and precise teamwork are critical, especially during high-tempo operations. The Yemen operation validated the F-35C's carrier suitability under combat conditions. Its flexibility, from stealth missions to heavier payloads, demonstrated how fifth-generation capabilities can be projected from naval platforms, extending precision strike reach without reliance on foreign bases. Mission execution details. The Yemen strike operation unfolded in a carefully orchestrated sequence, each phase building on the last to dismantle Houthi defenses while minimizing coalition risk. Phase 1. disabling air defenses. The operation began with EA-18G Growlers from the USS Abraham Lincoln, establishing electronic warfare barriers, using ALQ-249. Next-generation jammers, they disrupted radar networks across frequencies from 0.5 to 18 GHz, effectively neutralizing SA-2 and Fakur-1 systems. This cleared the way for F-35's Cs to penetrate undetected, targeting air defense radars and command nodes. Phase 2. Locating hardened targets. Houthi forces had adapted by dispersing mobile missile launchers and relocating command centers to underground bunkers, some buried up to 100 feet beneath Yemen's mountainous terrain. The F-35Cs employed their ANAPG-81 AESA radar in synthetic aperture mode to map terrain and identify concealed tunnel entrances. This capability proved critical for pinpointing targets hidden by camouflage or natural cover. Phase 3. Precision strikes. The strike package included BLU-109 bunker busters and GBU-31 JDAMs, with weapons tailored to target characteristics. Delayed action penetrators were used for underground facilities, while instantaneous fuse weapons hit surface structures. F-35s maintained stealth with internal weapons bays, though some operated in beast mode with external stores after air defenses were suppressed. Secondary explosions from ammunition depots and missile storage facilities lit up the night sky, with some detonations continuing for hours, an unmistakable confirmation of the strike's success. Phase 4. Sustained electronic warfare and egress. Throughout the operation, Growlers maintained jamming barriers and stood ready to engage emergent threats with AGM-88 GAARGMER missiles. The F-35C's distributed aperture system provided 360-degree situational awareness during egress, monitoring for potential missile launches. Thermal imaging from the EOTS system enabled battle damage assessment without requiring risky reconnaissance passes. The operation destroyed 85% of planned targets, including 3 underground command centers, 7 missile launch sites, and critical radar installations. Post-strike analysis confirmed the elimination of C-802 anti-ship missiles and CASF-2K drones, safeguarding Red Sea shipping lanes. This success demonstrated the power of integrating stealth, electronic warfare, and precision strikes, setting a new standard for future operations in contested environments. Strategic implications. The F-35C strikes in Yemen delivered a clear message about American military capabilities and regional priorities. Amid escalating Houthi attacks on Red Sea shipping lanes carrying 15% of global commerce, the operation underscored Washington's commitment to protecting vital trade routes. By targeting underground weapon storage facilities that had eluded previous air campaigns, the strikes addressed a critical gap in counter-Houthi efforts, recalibrating regional power dynamics without triggering wider conflict. Iran now faces a dilemma regarding its support for Houthi missile capabilities. The operation demonstrated the U.S.'s ability to locate and destroy deeply buried targets with minimal warning, undermining Tehran's proxy warfare strategy. Iranian-made C-802 anti-ship missiles and CASF-2K drones threatening maritime traffic were destroyed, forcing Iran to either escalate weapons transfers at greater risk or accept limits on its regional influence. This operation was akin to a surgical strike, precisely cutting away at the enemy's hardened assets while minimizing collateral damage. The combination of stealth penetration and precision targeting showcased the U.S.'s ability to neutralize fortified threats, altering calculations for actors considering attacks on international shipping or U.S. interests. The minimal civilian impact preserved diplomatic flexibility, avoiding the complications often associated with military actions in populated areas. The deterrence value extended beyond Yemen, highlighting how fifth-generation aircraft can project power without relying on vulnerable regional bases. The USS Abraham Lincoln's ability to launch complex strikes from international waters demonstrated strategic flexibility, reducing political constraints tied to ground deployments while maintaining a persistent threat response. Houthi forces had adapted to previous strikes by constructing underground bunkers and mobile launch platforms, but the F-35's precision munitions like the BLU-109 bunker buster bomb overcame these defenses. This technical solution resolved operational challenges that had frustrated earlier coalition efforts, signaling to regional actors the vulnerability of similar hardened sites. The operation also exposed the limitations of Russian-made air defense systems used by proxies, challenging Iran's reliance on such technology. Commercial satellite imagery confirmed the destruction of tunnel networks and ammunition depots, reinforcing the credibility of U.S. deterrent threats. By leveraging advanced capabilities with restraint, the U.S. achieved political objectives without escalating to full-scale war, preserving options for de-escalation or continued pressure in a volatile region. Technological arms race. The Yemen operation highlighted a stark technological gap between U.S. fifth-generation capabilities and adversary defense systems. Iran's air defenses, relying on Russian-designed platforms like the S-300, failed to detect or engage F-35's during the strikes. This failure underscores the limitations of older radar systems, which struggle to track objects with radar cross-sections below 0.1 square meters. The F-35's 0.005 square meter signature rendered it effectively invisible, demonstrating how advanced stealth technology can neutralize even numerically superior defenses. This asymmetry is akin to a modern-day David versus Goliath scenario, where cutting-edge technology allows smaller forces to outmaneuver and outmatch larger, less advanced systems. Russian-made air defenses, such as the SA-2 and Fokker-1 radars, have repeatedly underperformed against Western aircraft, as seen in Yemen and Syria. These failures raise doubts about the value of such systems, especially against adversaries equipped with fifth-generation platforms. For nations like Iran, the inability to close this gap forces reliance on asymmetric tactics rather than direct competition. Emerging threats like drone swarms further complicate the picture. Small, coordinated unmanned systems can overwhelm traditional defenses through sheer numbers and low observability. Iran's use of Shahed-136 loitering munitions exemplifies this challenge, creating a cost imbalance for defenders. In response, the U.S. has developed directed energy weapons and electronic warfare systems to counter these threats, showcasing the adaptability required to maintain superiority. Looking ahead, the U.S. is pursuing next-generation counter-stealth technologies while advancing its own stealth capabilities. Multi-band radar systems aim to reduce the effectiveness of current stealth designs, while research into sixth-generation aircraft promises even greater advancements. The EA-18G Growler's ALQ-249 jammer exemplifies this dual-track approach, disrupting enemy radar across a wide frequency range to protect stealth operations. The Yemen strikes demonstrated how technological superiority can achieve strategic objectives with minimal risk. By combining stealth, electronic warfare, and precision strikes, the U.S. achieved decisive results without prolonged campaigns. This model suggests future conflicts will hinge on technological innovation rather than sheer numbers. As hypersonic weapons, autonomous systems, and space-based capabilities emerge, the ability to integrate and evolve these technologies will define military success in the decades to come. The Yemen operation showcased how stealth, precision guidance, and electronic warfare can overcome modern air defenses. The F-35C penetrated Houthi defenses with support from EA-18G Growlers, while advanced munitions ensured success against hardened targets. U.S. military advancements like Block 4 upgrades for the F-35 and research into directed energy weapons aim to counter emerging threats such as drone swarms. These innovations highlight the need for constant evolution to maintain superiority. As technology reshapes warfare, one question remains: how will these advancements redefine global security? The future of military innovation depends on staying ahead, deterring aggression, and minimizing risks.